My name is Tomáš, and I would like to present you today the paper Smooth Approximations and Relational with Collapses that we have written together with Antoine, Mottet, Michał, Pinsker, and Michał, Wrona. We are dealing with constraint satisfaction problems in this paper, so let me shortly introduce what a constraint satisfaction problem is. So we are given a relational structure A over some finite relational signature, but possibly over infinite domain. And then the constraint satisfaction problem over A or CSPA, to shorten it, is then the following computational problem. We are given some variables set V, some finite set of variables, and some finite set of PP formulas over the signature of A that use free variables only from the variable set V. And PP formula here means just first order definable formula, not using universal quantifiers, disjunctions, or negations. Every such PP formula from this finite set will be called a constraint, and the question now is whether the instance of the CSP of A given by the conjunction of these PP formulas is satisfiable in A or not. Already in the name of the paper, there is mentioned something like relational width, and in order to define this notion, we need to understand the KL minimality algorithm. So let me shortly introduce this. K and L are some parameters, some natural numbers such that K is less than or equal to L. And this algorithm gets some instance of the CSP of A of some relational structure, and it does the following two things. First of all, it adds some domain constraint for every L element subset of the variable set V. And in the second step, then it reduces constraints by comparing projections of these constraints on subsets of the set of variables of size at most K. So this is some kind of local consistency checking, what we are doing here. And after running the scale minimality algorithm on an instance, we get a KL minimal instance that will still be an instance of CSP of A as we have defined it. Short example is if we are given some instance over with two constraints, phi and psi, and over three variables, say x, y, and z. And the first constraint is saying us that z is in between 0 or 1, and the second one tells us that z is either equal to 1 or equal to 2. Then what we do if we consider, for example, the 1-1 minimality algorithm, we just remove the possibility of z being equal to 0 from the constraint phi, and the possibility of z being equal to 2 from psi. And I promise you that using this scalar minimality algorithm, I will be able to define a relational width. So here it is. Given some relational structure A, we say that A has relational width KL if every KL minimal instance of CSP A that has satisfiable constraints is satisfiable. And we say that such relational structure has this bounded width if it has relational with KL for some parameters KL, and we don't care what the parameters are. What is maybe surprising, there are also different definitions of bounded width using, for example, logical definability, so the logic data log or some infinitary logics with bounded number of variables. Then there are also definitions using finite model theory, for example, the spoiler duplicator games. Or there are also different definitions using the notion of tree width of relational structures. And what is kind of clear is that if a relational structure A has bounded width, then its CSP is polynomial time solvable. Why is it like that? Because the only thing that we need, given an instance of CSP of A, is to run the scalar minimality algorithm, which is polynomial time, and then just check whether the constraints are still non-empty in order to know whether there is a solution to this instance or not. And let me introduce you shortly some examples of structure that have or do not have bounded width or relational width 2, 3. The first one is just maybe the easiest one. To just consider two element sets together with the inequality and equality relation, and it is kind of clear that it has relational width 2, 3 because the only thing that we need to check in order to check satisfiability of an instance of CSP of this structure is to compute transitivity. The other structure that has relational width 2, 3 for very much the same reason is just are rationals together with the usual linear ordering. And the last structure that I want to mention here is just a well-known computational problem 2SAT that has relational width 2, 3 as well. On the other hand, there are of course structures that do not have relation with 2, 3. Just consider Z2 with two ternary relations, where R0 and R1, where Ri just says us that the tuple ABC is in there if A plus B plus C is equal to I modulo 2. And I claim that this structure does not have relation with 2, 3, and why? We can ask why, but the answer is really simple. Just consider any I from Z2 and any A, B in Z2, then we of course can find C such that A plus B plus C is equal to I in Z2. But this in particular means that if we consider this instance of CSP of A with these two constraints, that this is still a 2, 3 minimal that has non-empty constraints, but it's not satisfiable at all because, of course, at the same time, it is not possible for x plus y plus z to be equal to 0 and to be equal to 1 over z2. And actually, if we restrict ourselves to CSPs with finite domains, so to relational structures with finite domains, then I would say relational width and bounded width are quite well understood. And this is actually due to Bartel, and the second part of this theorem is due to Bartel and Kožík. And this tells us that if we are given some relational structure over finite domain, then it's equivalent for it to have bounded width, to have relational width 2, 3, or to be preserved by M-array near anonymity polymorphism for every m greater or equal to 3. This means a polymorphism satisfying this nice set of equations. It follows that, for example, what I have shown you on the previous slide, the structure Z2 together with relations R0 and R1 does not have bounded width at all. But we are, of course, interested not only in finite domain CSPs, but what we want to understand is bounded width for some infinite domain CSPs. And now we may, of course, ask what the proper definition of some infinite domain CSP is, because if we, of course, consider just infinite structures or maybe even omega categorical structures, then we would obtain almost, if we want to classify the complexity of CSPs of such structures, this is actually almost impossible because almost all computational complexity classes that you can imagine could appear there. So we need to find some less general class of structures that we want to look at, and this will be so-called further redux of K-homogeneous L-bounded structures. What does it mean that structure is K-homogeneous L-bounded? K and L are again some natural numbers. So relational structure B is K-homogeneous if for all tuples AB of arbitrary finite length, A and B are in the same orbit of under the automorphism group of B, if and only if their K subtuples are in the same orbit under this group. And we say that such a relational structure is L-bounded if whatever finite structure X we take, that is, of course, in the same relational signature, the structure embeds to B if and only if all its substructures of size at most L embed to B. So actually, both K-homogeneity and L-boundedness are some kind of finiteness assumptions, and they are, I would say, kind of natural. And it may be that you have already heard about actually the notion of finitely bounded homogeneous structures, which is the more usual notion, I would say, for CSPs over infinite structures. But this is basically the same, because if you consider a finitely bounded homogeneous structure that's over a finite relational signature, then this structure is K-homogeneous L-bounded, where we just take K to be the maximality of its relations and L to be the size of the largest bound. So there is no problem with that. And but I promised you that we are interested in the first order redux of such structures, which is much more general class than just the class of K-homogeneous L-bounded structures. What is the first order redux of such structure? This is just a structure that has first order definition in some K-homogeneous L-bounded structure. And what is important to say, maybe on the first side, it is not clear whether this is some generalization really of finite domain relational structures, and it is, and it's not so hard to see. Say that we are given some relational structure A over finite domain consisting of the elements A1 up to AN. Then it's easy to see that this structure is a first order redux of a structure over the same finite domain that has n many unary relations, where every relation contains just the element AI. And this structure is one homogeneous and two bounded. So if we speak about first-order reducts of K homogeneous L bounded structures where K and L are arbitrary natural numbers, then we of course include also all finite or structures over finite domains. On the other hand, maybe you can ask whether we are or why we are actually interested in finite infinite domain CSPs, because of course finite domain CSPs are maybe easier to understand or easier even to imagine, but there are many problems actually that can be phrased as CSP, but that can be phrased only as CSPs over infinite domain. One of them is, and the easiest one is the diagram of acyclicity problem, but on the other hand, the same holds, for example, for linear programming or for some reasoning problems in artificial intelligence. So there are good reasons to be interested in this generalization of finite domain CSPs, and this is what we want to do. Okay, and actually, as I have already mentioned, finite domain CSPs are well understood. So we know this nice algebraical characterization of bounded width. This is due to Bartow and Kozik. We know also the characterization of finite domain CSPs that are polynomial time solvable. Of course, under the assumption that P is not equal to NP, they are characterized by the existence of this Siggers polymorphisms. This means that by the existence of some 6-array polymorphism satisfying this nice equation. This is actually due to Bolatov and Zhuk in 2017. It was proven, and this actually proves also the famous Feder and Barde dichotomy conjecture for finite domain CSPs. And we have similar conjecture for infinite domain CSPs. This is due to Bodilsky and Pinsker and this formulation using pseudo-Siggers polymorphisms. This is due to Bartow and Pinsker. So we say that if A is a first-order reduct of a K homogeneous bounded structure B, that is a core. And of course, if we suppose that P is not equal to NP, then we would like to prove that the following are equivalent, so that the CSP of A is polynomial time solvable, or that A has a pseudo-Siggers polymorphism modulo the closure of the automorphism group of B. What does it mean having a pseudo-Siggers polymorphism? This means having a 6-array polymorphism, again satisfying this nice equation where we compose both sides with some elements alpha and beta from the closure of the automorphism group of B, where the closure is just the set of all unary functions that agree on every finite domain with some of these automorphisms. And okay, so there is at least a hope for a nice characterization of polynomial time solvable CSPs over infinite domains. But what about bounded width? We saw that there is nice characterization over finite domains, and maybe there is also some other one, some nice characterization also over infinite domains. So maybe can we take pseudo VK news? So we have taken their pseudo-Siggers polymorphisms, so composing these Siggers polymorphisms with some elements of the closure of the automorphism group of B. Can we do something similar in here? This is a reasonable question, but the answer is unfortunately no. No, not in general, at least. And the counter examples are just reducts of the rational numbers because for them there is no set of identities that would characterize bounded width, and this result is due to Bodilsky, Pakusa, and Rydval from 2020. On the other hand, there are good news as well, otherwise I wouldn't speak about it. And this good news are that for many other structures this is actually enough. An example is, for example, the universal homogeneous graph and its redux, or universal homogeneous tournament and its redux. And this is actually due to Mottet and Pinsker, where they were able to prove this using their celebrated theory of smooth approximations. And the reason why this holds actually for these structures is that they have not only pseudo-weak and new polymorphisms, but even canonical ones. And what does it mean for a polymorphism of relational structure to be canonical? This means that we say that it is canonical modulo the automorphism group of B, where B is this K homogeneous about the structure, if it preserves the orbital equivalence modulo the automorphism group of B, which happens actually if and only if it induces an operation on the orbits of n2 plus for every n greater or equal to 1 modulo the automorphism group of B. So this means actually in some sense that we can then reduce to finite case. This is maybe not so easy or so clear on the first side, but this is possible. This is also a result proven several years ago. And this is also the reason why we are interested in these polymorphisms. And actually, canonical polymorphisms in general play a key and important role in all known complexity classifications of infinite domain CSPs. Okay, so we have seen that there is no algebraic characterization, nice algebraic characterization of bounded widths for redux of k-homogeneous bounded structures. But this still does not mean that there is no collapses for the finite case, so that we cannot say that whatever k and l we take, then every reduct of k-homogeneous bounded structure that has bounded width has a relation with, say, 34 or 57 or whatever. Unfortunately, this is also not possible, and this result is due to Grohe from the year 1994. On the other hand, we are actually able to prove some particular collapse, in the case where we fix k and l. So if we fix k and l, and A is a first order reduct of a k-homogeneous bounded structure that is preserved by these nice canonical pseudo-weak NU polymorphisms modulo the closure of the automorphism group of B, then it has relational with 2k and maximum of 3k and l. Note that this again generalizes the result for the finite domain CSPs, because as I have already mentioned, every finite domain CSPs is a reduct of one homogeneous two-bounded structure, and if you plug in it here, you exactly obtain that if it has bounded, it has relational with 2, 3. And it's not so hard to prove also from our proof that there is strong variant of the theorem if you replace canonical pseudo-weak NUs by pseudo-totally symmetric canonical polymorphisms. And this result actually enables us to obtain a collapse for first order reduct of many interesting structures. So for example, for the redux of the universal homogeneous graph, they always have relational with 4, 6 if they have bounded width. The same holds for the redux of the universal homogeneous tournament. If we consider the Hansen graphs, so the k and 3 graphs for some n, then their redux always have relational with 2n if they have bounded width. If we consider just natural numbers with equality, their redux, the redux always have relational with 2, 3. If they have bounded width, the same holds for the countably infinite equivalence relation with infinitely many equivalence classes. And the same holds for the universal homogeneous partial order, and so on. And actually, in all these cases, we can even prove that this bound is tight in the sense that there really exists some reduct of the structure that really has relational with, say 4, 6 in the case of the universal homogeneous graph, but it does not have relational with some small relational with, so say relational with 3, 5. And actually, such example I want to really briefly present you of a reduct of the universal homogeneous graph. So I will denote by E the edge relation and by N the non-edge relation. So this means the relation saying the two elements are not equal, but there is no edge in between them. And A will be just the first order reduct of this universal homogeneous graph with two quaternary relations given actually by this simple picture. R equality just saying that the edge status of A and B is the same as the edge status, so-called, to say it like that, of C and D. So this means either there is an edge between the first two elements and an edge between the second two elements, or vice versa. And our inequality says exactly the opposite. So there is an edge in between A and B if and only if there is no edge in between C and D. Now this kind of easy instance of CSP of this relational structure A is 3k minimal for every k greater or equal to 3. It has non-empty constraints, but it's not satisfiable at all, which is easy to see. It's also possible and not so hard to find an instance that is 4, 5 minimal and not satisfiable at all. So it follows that the exact relation of it of A is 4, 6, because we can show that A is preserved by these nice pseudo-weak NUs that are canonical modulo the closure of the automorphism group of B. And I should also mention that this example was for the first time discovered by Michał, and but it really fits well to our purposes of this to show that there really is the bound for the redux of the universal homogeneous graph is really tight. And now I would like to also shortly mention the other results that we were able to show in this direction. So if we consider redux of unary structures that are coarse, so whatever unary structure we take, then bounded width is again characterized by canonical pseudo-weak and use modulo the closure of the automorphismal group of B. And if they have bounded width, they have relational width at most 4, 6. But attention here, this is the only kind of structures where we cannot prove that this bound is really tight. So we don't have a proof that there exists such a structure having a relational width 4, 6 and not less. We actually think that this is not the case. And the same we are able to prove for CSP's modeling model checking problem for MMSNP sentences. But what is interesting, of course, in here that it follows that the data log rewritability problem for MMSNP is decidable, and this problem is 2nx per time complete, which answers also some question that was asked several times before in the literature. And finally, of course, we were able to prove something, but there are still many open questions and maybe even more after this. So the first one and the maybe most interesting one in this direction is, of course, if this collapse holds for all for the redux of k-homogeneous L-bounded structures. This could be the case. This does not have to be the case. We don't know. We don't have any counterexample, but we are also far from having a proof. The other question, of course, interesting that in this direction would be which intermediate relational widths are possible for first order redux of a particular k-homogeneous L-bound structure. So, because what I have forgotten also to say that if we have finite domain CSPs, that a structure that has bounded width, then it has relational width, exact relational with either 1, 1 or 2, 3, nothing in between. Here we know, for example, for redux of the universal homogeneous graph, they have relational width at most 4, 6. But maybe there is some redux having a relational with 3, 5. Of course, there is redux having a relational with 2, 3, redux having a relational with 1, 1. But what are there other relational with possible? Who knows? And the last question that I want to present here is, of course, to know for which structures actually our result implies, and not only for which structures our result implies, but for which structures actually the bounded width is characterized by the existence of this nice pseudo-weak NUs. Okay, so this was everything from my presentation. Thank you very much for your attention.